last time we tried to derive the expression for the specific heat that contributes from phonon. And this is, what we have left last time at the end of the lecture, that the CV is given by this integral over this frequencies or energies, and inside this integration we get this kind of dE bar dt, which is the temperature derivatives ensemble average of the total energy of the phonon Hamiltonian, and d of omega is the density of states of the phonon mode within the Debye approximation, where we get a quadratic dispersion of the phonon mode and up to kind of Debye frequency. Okay, so the actual profile of this density of states is kind of messy shape, but within this Debye model, we could approximate this kind of a dispersion relations in the frequency domain as omega squared multiplied by some prefactor. Remember that. And this prefactor is given by this factor, which was assigned to you as a homework problem. Okay, so now let's finish this calculation. We could define the dimensionless variable x, which is h bar omega divided by kBt. Suppose we define such a x variable, and we can change this integration, the omega, into the integration over the dimensionless quantity x, multiplied by some kind of a temperature prefactor. So, and this is what we get if we change the variables from this the omega to the x, and omega runs from, say, 0 to Debye frequency, so the x variable runs from 0 to theta over t, where theta is called Debye temperature. And we know that the Debye temperature is really, really high, which is almost a few hundred Kelvin, and so the temperature range that we're interested in is always much lower than the Debye temperature. So T should be much lower than the Debye temperature. In such a case, the x, the upper bound for this x integral, theta over t, is very, very large, which is almost infinity. Okay, so when temperature is much lower than Debye temperature, this integral can be approximated in terms of the integration over x from 0 to infinity, because theta over t is almost infinity. And this dimensionless integration over x is a number. It's just a factor, prefactor. And we simply just check the stable integration to get this number. And we plug that in. The final result for the specific heat contributed from phonons given by 234 times n kb times t over theta cubic. Okay, so that's the temperature much below Debye temperature, theta, and the specific heat is given by this T cubic behavior. And remember that in our high school, we know that the specific heat of the classical, say, particle molecule is given by 3 times n times kb, where n is the number of particles. So we can combine the contributions for the specific heat from the phonons and from the electrons, electronic. Remember that we already calculated this gamma coefficient, which contributes from the electronic density states that contribute to the specific heat. Okay, and the specific heat contributed from the electronic part is actually linear in temperature with a prefactor gamma, which we call this specific heat coefficient gamma. And now we add the phonon contributions to the specific heat, which is T cubic term with a prefactor B. So in most metals in solid state systems, we have these 2 contributions with different power laws, And if we plot the CV over t against t squared, we get a straight line with a slope which is b and an intercept which is gamma. And this is precisely what happens in metals. And at low temperatures, CV over t shows a straight line with respect to t squared with the intercept gamma and the slope b. And both gamma and b could be measured experimentally in a very accuracy. So how do we measure this dispersion relations for phonon mode? And as we mentioned already, neutron scattering could be one possible way. So the neutron beams carry energy or frequency omega and momentum k, hit the target, and it gets scattered by this electrons and phonons inside this material, and the outgoing neutron beams carry frequency omega prime and momentum k prime, and there is a momentum transfer between the incoming and outgoing momentum, which is defined as q. And this neutron beam can actually absorb or emit the phonon during this inelastic scattering processes. And there are two conservation laws. First, the conservation of the crystal momentum, and which says it's momentum k plus a reciprocal lattice vector. G is given by k prime plus or minus phonon. So which means that the phonon could be absorbed or emitted by this neutron beam. And energy conservation also help us to link this initial and final kinetic energy. So the total kinetic energy is conserved. The initial kinetic energy is given by this h bar squared k squared over 2m, and the final one is given by the kinetic energy of neutron being carrying momentum k prime plus or minus h bar omega, which is the absorption or emission of a phonon energy. Okay, so you can solve this too, and you can take the data omega prime and k prime, and you can change the angle of your detector to actually see how this neutron beam gets scattered, and then you could get information for the omega as function of q. Okay, so let's continue to go beyond the harmonic approximation. As I mentioned earlier, that harmonic approximation, we assume that phonons are free and there are no phonon-phonon interactions, if therefore the phonons do not decay. Okay? And there's no mechanism within the harmonic approximation that could explain the thermal expansion of a solids. And there's no mechanism to describe the collisions between the phonons, because phonons are non-interacting. They are free, and also at high temperature, CV is a constant. So the first, second, and fourth results from the harmonic approximation are actually non-realistic at all, okay? Because we know that phonons are interacting with each other, and we know that in solids we have a thermal expansion. We know that phonons can collide with each other and interact with the all other atoms and also phonons, so that we have a finite lifetime of phonons. And we could explain the thermal expansion of solids because of the phonon-phonon interaction, and we know that phonons interact with the other phonons in solids. It's just that the harmonic approximation cannot capture that coupling between phonons and phonons. Okay, so that in order to capture the interactions among phonons, we need to go beyond the second order harmonic approximation that we do here to the higher order so-called n-harmonic terms in the potential. Okay, and we will do that now, okay, in order to capture more realistic phenomena in solid state. So this is the potential up to second order harmonic approximation that we did, and we now we add the third order term to the potential, so that the white curve now becomes a yellow dashed line. Of course, it got shifted and distorted, but basically you still get some minimum point right here. Okay. However, we get the third order term in this perturbed expansion of the phonon displacement vector, and that third order term turns out to be very important to reach the thermal equilibrium and to explain the thermal expansion of solids. So such term in terms of displacement vector is given by this yqi, yq prime j, yq double prime k times this Fourier phase vector and the matrix element vijk, L prime, L double prime, which is similar expression as we did for the second order harmonic approximation. It's just more complicated. It involves, say, more degrees of freedom. It involves 3 displacement vector and multiply together, so we get tensor-like product. And also the matrix element involves 6 indices. Okay, so we could simplify this Fourier expansion of the third order, and we could just come up with the resulting expression here that we sum over L and L prime and L double prime, and we could just come up with such a simplified version of the Fourier coefficient, and we can take advantage of such identity which we'd introduced earlier, saying that if we sum over L from 1 to n, this exponential factor e to the iq dot L, and this is going to be n, or sum over 1, sum over L and 1, L runs from 1 to n, which is, and if this q is the same as the reciprocal lattice vector g, and 0 if they are not the same. And therefore, we could take advantage of such a result, and we define this as n times a generalized delta function, which is sum over reciprocal lattice vector g with a delta g and q, which we denote this as capital N times this delta as function of q, which we call the generalized delta function. Okay, so let's call it a day, and next time we will start from this third order n-harmonic term, and we can second quantize this, and we can discuss the interactions among different phonons. And use that picture, we could explain the decay of phonons and the thermal expansion, and also the thermal equilibrium of solids due to this phonon-phonon collision. Let's call it a day, and we'll see you online next week.